Hi everybody, welcome back. We've just got a few more chemistry lessons this year, and today we are continuing our study of acids and bases, learning about what happens when you combine them. So I'll share my screen here, and we're going to learn about 9.3, acids and bases, acid-base reactions. All right, our aim is 9.3. What happens when an acid and base combine? After the question of the day and going over the homework, I'll teach you about acid-base reactions. Then we'll start homework 21. All right, this question of the day is from a mini lab that we didn't get to do in person, but I think you'll be able to figure it out anyway. It says, to maintain the health of fish in your tank, you test the pH of the water using bromothymol blue indicator. A sample of the water turns yellow with the addition of the indicator. What do you think is going on in the tank? We learned that litmus paper turns red when it's in an acid and turns blue when it's in a base. That's one example of a pH indicator, but there's lots of others. And if you did the red cabbage mini lab, you know that other indicators can turn different colors. This one, bromothymol blue, turns yellow when it's in an acid, green when it's in something neutral, and blue when it's in something basic. So in this case, the fish tank water turned it yellow. So what do you think is going on in the tank? Well, clearly there's an acid involved. But why is there acid in your fish tank? You might be wondering. Well, taking a look at the reference table of common acids, you'll notice that one of the acids is CO2 aqueous, also written H2CO3 aqueous, and that's known as carbonic acid. What do you think fish are exhaling all the time? That's right, carbon dioxide. And when it mixes with water, it turns into carbonic acid, which is the same reaction that's happening in our oceans all over the world. But in this case, it just means it's time to clean your fish tank. All right, taking a look back at our homework, the first question was about strong versus weak. So they told us the acid HCl is strong and that the base NH4OH is weak. So we use that to answer these questions. So for 1B, which ions will NH4OH produce in water? Well, it's a base, so I know it'll make hydroxide ions. Part D, will it ionize completely, some, or very little? Very little, because it's weak. And then for part F, the name, I found those two ions on the table E, selected polyatomic ions, but I also happen to know them, but they're just called ammonium and hydroxide, so ammonium hydroxide. For number 2, naming acids or bases, either you can find these on your reference table and or you can use the rules we learned in class. So the first one, HBr, we're going to say hydro, then change the name of the element ending to ic, and then add the word acid. So it's hydrobromic acid. C is a base, so you just say the name of the two ions, lithium hydroxide. E is on your reference table, that's nitric acid. Number 3, strong acids and strong bases are strong blanks because they release large numbers of ions in water. That would be the really good conductors, or in other words, strong electrolytes. And for this last one, number 5, that should say, not A, a student tests the conductivity of 2 liquids. In liquid A, the light bulb barely lights up. In liquid B, the light bulb burns brightly. The student decides that A must be a base and B is an acid. Common misunderstanding. People seem to remember that acids conduct, but they forget that bases do too. The reason that strong acids and strong bases are such great conductors is because they make so many ions. So is the student correct? No. How can you tell? Because acids and bases conduct. And C, what can the student infer from this test? That B is a stronger electrolyte than solution A. And then in these last ones, we were identifying electrolytes. So 8, the one that's an electrolyte that will conduct, is the one that is a strong base, potassium hydroxide. This won't make ions, this won't make ions, this won't make ions, because these all have strong covalent bonds holding them together. This one is ionic, a base, and it's called potassium hydroxide. All right, our aim for today is 9.3, how do acids and bases react? So we're going to take a look at this video to see what happens when an acid and base are combined. But I'd like you to take a guess while I'm getting that set up and just think to yourself, what do you think will happen? Here we go. So equimolar solutions means you have the same number of moles of acid, same number of moles of base. I just added a pH indicator to the acid that's called universal indicator. And they're adding that same indicator to the base, sodium hydroxide. So the indicator is showing that they have very different pHs. So HCl is a little less than 3, and AOH is more than 11. Pretty wild that you can mix something pink and purple and it turns green, right? That's because the substance created was neutral. Cool. So why is it that when you combine an acid and a base, it makes something neutral? Well, let's see what's going on the atomic level. Okay, here on the left, we have HCl. On the right, we had NaOH. Boom, they recombine. What do we have now? H2O and, oops, I need to go back up and pause it, NaCl. So H2O, pure water, that's neutral. NaCl, you guys know, is table salt. That's also neutral. So the two things created are both neutral, so the solution is neutral. When you mix an acid and a base, you make salt water. Let's take a look at this in another way. Well, first I wanted to ask you this question. Why do you think it's called a neutralization reaction? It's making the acid and base neutral, pH 7. So neutralization is the name for this type of reaction. You might have also noticed when you were looking at it that it looked kind of like a double replacement. And yes, it is. It's like a subcategory of a double replacement. Neutralization. And a neutralization is always the same formula. Acid plus base makes salt and water. Now, because it makes the pH closer to neutral. Now, the salt created is not always NaCl. It really depends on which kind of acid, which kind of base you're reacting. But it's always a salt, which is a chemistry term that simply means an ionic compound. An ionic compound. So table salt is an ionic compound, sodium chloride, but anything where you have a metal plus a nonmetal is called a salt in chemistry. All right, there's 3 ways to write this neutralization reaction, and actually any double replacement or single replacement. But we didn't get to it then, we get to it now. So I want to take a closer look at this diagram. So our equation is HCl aqueous plus NaOH aqueous makes H2O liquid and NaCl aqueous. So let's find our reactants. Let's find the hydrochloric acid and the sodium hydroxide. So where's the hydrochloric acid? All right, here's the H plus, here's the Cl minus. So we can see that the H plus and Cl minus already broke apart. That's because it's a strong electrolyte. The ions break in water. How about the NaOH? Well, here we've got the Na And then here we have the OH. So same thing, it already broke apart in water. All right, let's take a look at our product side. What do we have here? Well, here we've got some little Mickey Mouses. H2O, that's water, water, water. And then here's the Na still floating around. Cl minus still floating around because that bond is ionic and breaks in water. So they're not going to stay together either. So do you notice anything funny? Anything that actually doesn't change throughout the reaction? Okay, that's good. We're going to get to that in a moment. The next way to write the reaction looks very intimidating at first. This is called the complete ionic equation. This is where you draw it how it really is. You see how the HCl is separate and the NaOH is separate? That's because it is in real life. HCl, as soon as you put it in water, is not HCl, it's H plus and Cl minus. So it's written that way in the ionic equation. Same with the sodium hydroxide. The water is still written together because that's a molecule. Strong covalent bonds, they'll stick together in water. But the Na and the Cl, that bond will break in water. So what do you notice about the Na and the Cl, the sodium and the chloride? You notice they don't do anything? They don't change. They were ions floating around in water before, and they're still ions floating around in water afterwards. There's a name for that, and that's called a spectator ion. They're just sitting on the couch. They're there, but they're not reacting. They're not breaking or making bonds, so that means they're not chemically changing. So the last way to write the equation is the true chemistry, getting at what's actually changing, and that's called the net ionic equation. So we cross off all the spectator ions and see what we're left with. What's our net? So our net ionic equation is just H and OH make H2O. And guess what? That is almost always the net ionic equation for any neutralization reaction. Acids always give the H plus, bases always give the hydroxide, and it always makes water. And then the salt are the spectator ions. So let's take a look at how to rate a neutralization reaction. So here we've got two reactants, HNO3 and KOH. So we're going to start with the generic word formula, which is acid plus base always makes water and a salt. Let's identify next our acid. Here it is, nitric acid. And here's our base, potassium hydroxide. So acid, HNO3 plus base makes water, H2O, and some kind of salt. Not going to be NaCl in this case because that's not what we started with. So let's see. The base gave away the hydroxide to make water. The acid gave away hydrogen to make water. What do we have left? Well, from the base we have a K plus, and from the acid we have an NO3 minus. So those two together are going to be our salt. So it'll be KNO3. Great. Let's try another one. Ooh, this time they wrote it in words. Lithium hydroxide and hydrobromic acid. Well, we will start off with our generic formula again. Acid plus base make water and a salt. So here's our acid. Hydrobromic acid is HBr. Our base is here. Lithium hydroxide is simply LiOH. Acid plus base makes water, H2O, and salt. So let's see what our salt is. Well, the base gave away the OH, leaving the Li. The acid gave away the H, leaving the Br. So there's our salt. Lithium bromide. And if you don't offhand know the charges, it is good to look them up to make sure that the compound you write is real and balanced for charge. Okay, I happen to know lithium bromide is good the way it's written, and same with potassium nitrate. All right, so let's try one more. We're gonna this time write the full ionic equation, then cross off the spectator ions and see what we have left in a net ionic equation. So this one is KOH and HF. Okay, so let's write our acid, HF, but we're gonna show it split apart into ions for the complete full ionic equation. H plus F minus. Okay, our base is KOH, so that'll be K plus OH minus hydroxide. Makes water, H2O, and the salt, so that'll be the K and the F. But split apart still. All right, what do we get to cross off? F didn't do a dang thing. Neither did K. What do we have left? H plus OH minus makes H2O. Neutralization. All right, last question. What do you think are the products of a reaction between KOH and HCl? All right, this is a classic acid-base neutralization. We've got KOH, our base, and HCl, our acid. We know that acid plus base make water and a salt. In this case, our salt will be the rest of the base, K, the rest of the acid, Cl. So here we go. Water and salt. Ta-da! Awesome, you guys. Tonight's homework is homework 21. Thanks for listening. I'll see you next time. Let me know if you have any questions.